In this set of videos, we focus on one of the most important areas of computer science and programming, algorithms. In this particular video, we're going to be looking at Dijkstra's shortest path algorithm. The purpose of Dijkstra's algorithm is to find the shortest path between one particular start node and all the other nodes in a weighted graph. This is similar to a breadth-first search, and you may recognise this diagram from our video on graphs. Before we get going with this algorithm, notice the table on the right. We've pre-populated it with the name of all the vertexes, A to E. The use of a table like this, or an array, which is how we might do it if we were programming it, is just one approach to programming Dijkstra's algorithm. It is possible to do this with a queue structure and a series of lists as well. So you'll find that most texts start with their demonstration of the vertex A. We're just going to mix it up a little bit and start with C and show you how you can find the shortest path to all the other vertexes or nodes in this graph. Now notice we've put some additional data into our array. We've said that all the nodes are not visited, and we need to set an initial starting shortest distance for each of the vertexes as well. We need to pick a very large number, so traditionally we pick the largest of all numbers, and that would be infinity. Notice that the shortest distance from our starting vertex C is going to be 0. So the first thing we're going to do is recognise all the unvisited nodes from our starting node. So A and D are both connected to C, and they are not visited. So we'll just deal with them one by one, and we'll start with A, since it's at the top of our array. And so what we're going to do is calculate the distance from A to the start C. And that's what those numbers are on the edges. So we know the distance from A to C is 2, but we calculate it as 2 plus the shortest distance from the node that we've come from, which is C. And the shortest distance from C was 0. So it's actually 2 plus 0 equals 2. We then look at D, and we say D to C is 5. 5 plus the shortest distance from C, 0. 5 plus 0 is 5. So we can now complete our table with this information, and C has been visited. Now, one important thing to note is that we updated the shortest distance for A and D in our table to 2 and 5 respectively. But we only did this because the number was smaller than the number that was already in that place, which was infinity. So 2 was less than infinity and 5 was less than infinity. So we updated our table from that data. The other thing that we've done is we've recorded the previous vertex that we came from. So we came from C in both situations. We're now ready to identify our next node. And what we do is, looking down our array, we identify a node that has not been visited but has the shortest distance from the start. So in this case, it would be A with the shortest distance from the start of 2 that we're going to visit next. So we identify all the nodes that are connected to A that haven't already been visited. And in this case, because C has already been visited, the only other connected node is B. So now we calculate the distance from B to the start. So that is the distance between B and A, which is 8, and the distance from A to the start, which is 2. So we've got 8 plus 2 is 10. We now look at the shortest distance from the start for B and see if 10 is lower than the number that we're already storing. Well, 10 is less than infinity, so we can update that data and also the previous vertex that we came from for B, which was A. We can now mark A as visited and we can have a look at the next node that has not been visited with the shortest distance from the start. So we're looking through our array and we discover that D is the next node that hasn't been visited with the shortest distance of 5. So that's the next node that we're going to consider. So the first thing we do is identify the nodes that are connected to D that have not already been visited. And those would be B and E, because C has already been visited. So taking them in turn, and we'll just do them in the order in which they appear in the array, we're going to calculate the distance between the node that we're going to and the start. So if we consider B, the distance between B and D was 9, but the shortest distance from D to the start is currently 5. So 9 plus 5 is 14. And we're going to look to see whether 14 is less than what we're currently storing as the shortest distance from the start for B, and that's 10. Well, 14 is not less than 10, so we're not going to update the data in our table. This is really important if the algorithm is going to work correctly. So the next node that we're going to look at then is E, and we're calculating E to D is 5, plus D's distance to the start, which is 5, so that's 10. So we consider whether infinity is more than 10. Well, it is. 10 is less than infinity, so we can update the shortest distance from the start for E to 10 and record the previous vertex as D. So at this point, D has now been visited, and we can look down our array for the next node that hasn't been visited with the shortest distance from the start. Well, we can see that that's B and E. It doesn't really matter which one we're going to choose here, but logically you'd probably pick the one that's at the top of the array, so we'll go for B. So hopefully by now you'll have noticed that actually there's a pattern to this algorithm, and it's very simple to code just with a series of conditions and iterations. Anyway, the only node that B is connected to that has not already been visited is E. So we calculate the distance between B and E as 4, and the distance from B to the start is 10. So 10 plus 4 is 14. Is 14 less than 10 that we're already storing for E? No, and therefore we're not going to update our data. And we can say that B has been visited. So at this point we're going to look down our array for the next unvisited node with the smallest shortest distance from the start. Well, there's actually only one left, and that's E. So E is the next node that we're going to consider. Now E does not have any nodes connected to it that haven't already been visited. Therefore we can update our array just to say that E has now been visited. We now look down our array for the next unvisited node with the shortest distance from the start, and we can see that there aren't any because they're all visited. Therefore, our algorithm is complete. Let's have a look at how we can make use of the data that the algorithm has generated. So remember that the purpose of Dijkstra's shortest path algorithm is to find the shortest path from one node to all the other nodes. It won't tell you, for example, the shortest path now between B and E because we started with node C, but it will tell you the shortest path from C to the other nodes. So let's assume that we were going to try and find the shortest path between C and E. What we do is we look at vertex E in our array, and we can see that its previous vertex was D. So we can then go to D, and we can see its previous vertex was C. So we found the shortest path between C and E. It's C, D, E. And if you have a look at the graph, this rule applies to any other node from C as well. If we're looking for the shortest path between C and B, then we look at B in our array, and we can see that the previous vertex from B was A. and from A to C. So the shortest path between C and B is via A. Now, if there happen to be more than one shortest path with the same shortest distance, then this algorithm is just going to show you one of the possible routes. Don't be confused about that. So how can this algorithm be put to better use? Well, here's an abstraction of a map of the county of Gloucestershire, and some of the areas of Gloucestershire have been highlighted on the map. Not all, but just a few for the purposes of this illustration. So imagine we were trying to find the shortest route between Tewkesbury and Stroud. Should we travel via Gloucester and then to Stroud, or to Cheltenham and then to Stroud, or to Cheltenham and then to Gloucester and then to Stroud, or perhaps Tewkesbury to Cheltenham to Cirencester to Stroud? Dijkstra's shortest path algorithm will answer that question for us. So if we create a graph with this data, and we know the miles between each of the points, then we can create the data structure we need to apply the algorithm to it. And using abstraction, because we don't need the unnecessary detail of the actual map, we can just look at the nodes and the edges. So here is that graph. And we've set up a new array, and we've set all the nodes or vertexes to be unvisited. We've set the shortest distance from the start to be infinity for all the nodes except for our starting node, which is T for Tewkesbury in this case. So we're going to identify the unvisited nodes from T, and in this case they are C and G. And we're going to calculate the distance from C to the start. So the distance from C to T is 9, and the distance from T to the start is 0. So 9 plus 0 is 9. We check this against the shortest distance from the start for C that we're storing already, and we can see that this is infinity. 9 is less than infinity, so we can update the shortest distance from the start for node C. We can also do the same for G. So the distance between G and T is 13, and the distance from T to the start is 0. So 13 plus 0 is 13. This is less than infinity that we're storing for G already, so we can update the shortest distance from the start for G to be 13. We can also update the previous vertex for C and G to both be T as well. So T is now visited, and we can look for the node that's got the shortest distance from the start that hasn't already been visited. And we can see from the array that that would be C with a shortest distance of 9. So C is the node that we're going to look at next. So C is connected to 3 unvisited nodes, G, I and S. So we calculate the distance between C and G is 8, and the distance from C to the start is 9. So we've got 9 plus 8 is 17. So we have a look at what we're storing for G already, and we can see that it's 13. Well, 17 is not less than 13, so we're not going to update the data for the shortest distance for G. Now we consider I. The distance between C and I is 15, and the distance from C to the start is 9. So 15 plus 9 is 24. So we look at what we're storing for I already, and it's infinity. So 24 is less than infinity, and we can replace the shortest distance from the start for I with 24. We now consider node S and calculate the distance between C and S is 14, plus the distance from C to the start, which is 9. So 14 plus 9 is 23. Looking at what we're storing for S already, we can see that 23 is less than infinity, so we'll update the shortest distance from the start for S to 23. We can now say that C has been visited and look down the array for the next node that has not been visited with the shortest distance from the start. And we can see in this case that it's G with 13. So G is the next node that we're going to visit. At G, we can identify there are two further nodes that have not already been visited. Those are B and S. So we calculate the distance between G and B is 17, plus the distance from G to the start is 13. So 17 plus 13 is 30. 30 is less than infinity for the shortest distance from the start for B, so we can replace infinity with the number 30. We can now consider S. So G to S is 10, plus G's shortest distance already is 13, so 13 plus 10 is 23. Well, 23 is the same as the shortest distance we're already storing for S, so there's no need to update it. Now notice we're updating the previous vertex as we're going along here if we're updating the shortest distance. It's important not to forget that step. So G has now been visited and we can look for the next unvisited node with the shortest distance from the start. Looking down the array we can see that's S with a shortest distance of 23. So S is the next node we will consider. So S has two unvisited nodes connected to it. Those are B and I. The distance between S and B is 14 and the distance from S to the start is 23. So 23 plus 14 is 37. 37 is not less than 30 that we're already storing for B, so we're not going to update that. Now we consider I. The distance between S and I is 15 and the distance from S to the start is 23. So 15 plus 23 is 38. We're currently storing 24 for I and 38 is not less than 24, so we're not going to update the data. And we can consider S now visited. Looking down our array we can identify that the next unvisited node with the shortest distance is going to be I with 24. So I is the next node we consider. Now I is not connected to any nodes that we haven't already visited, and therefore we can simply update it as visited. We now look at the array for the next unvisited node with the shortest distance from the start, and we can see that must be B because there's only one left and it has a shortest distance of 30. So B is the next node that we're going to consider. Now B is also not connected to any unvisited nodes because it's the last one, and therefore we can simply say that it has been visited. So looking down the array we know that there are no more unvisited nodes and therefore the algorithm must be complete. So we can now use this data and answer our question, what's the shortest path between Tewkesbury and Stroud? Is it via Cheltenham to Stroud or Gloucester to Stroud or another combination? So Stroud is where we want to be, and therefore we look at that in the array and we identify that the previous vertex from S is C and the previous vertex from C is T. Therefore the shortest distance must be T to C to S. Now, as it happens in this particular example, if you look, there is another solution to the problem. So we could also go from Tewkesbury to Gloucester to Stroud, and you'll see that it actually has the same shortest distance. But use the data to have a look at other possibilities, and you'll see that Dijkstra's algorithm is a great way of finding the shortest path between 2 points, or between one point and any other point on the graph. Now a final afterthought is because we're using abstraction here and it's only the data in the graph that actually matters, we can rearrange these towns and cities in Gloucestershire however we like as long as the data doesn't change. It doesn't actually have to match the pictorial view of the map of Gloucestershire at all. This is a powerful example of abstraction in process.